Hey there, curious minds. Welcome back to the Deep Dive. Today, we're pulling back the curtain on one of those unsung heroes of networking.
Oh, yeah.
A protocol that works tirelessly behind the scenes in pretty much every network you touch, but, often goes completely unnoticed. We're talking about DHCP.
DHCP. Yes. It's truly a foundational piece, isn't it? Sort of like the internet's plumbing.
Exactly.
And because it just works so well most of the time, it's really easy to just take it for granted.
Right.
But getting your head around DHCP, it doesn't just demystify how your phone gets online, It unlocks a much deeper understanding of network architecture itself, reveals how devices talk to each other, how administrators sort of orchestrate these, well, complex digital spaces.
Absolutely. And that's our mission today, to really demystify this dynamic host configuration protocol, DHCP. We've got this fantastic, really comprehensive technical guide here, and we're going to use it to explore everything. I mean, from the moment your phone grabs Wi-Fi, all the way to the pretty sophisticated setups network admins use to manage, like thousands of devices.
What's really fascinating to me is just how much complexity DHCP handles automatically. It's like having this incredibly efficient, tireless network librarian.
Librarian, I like that.
Yeah, who doesn't just assign every new book a unique number and IP address, but also tells it exactly where its section is, who its neighbors are, how to find other libraries. It just removes this huge amount of manual work.
Okay, that librarian analogy, that's perfect. Let's unpack this silent organizer, this librarian, starting with the basics, so DHCP. We throw the acronym around. But for someone who maybe knows the networking fundamentals, what's the deeper story? What is it actually doing, and why is it so critical?
Well, fundamentally, DHCP, it builds upon something a bit older called the Bootstrap protocol, BOOTP.
BOOTP, right.
Think of BOTP as sort of the initial, simpler set of instructions. It was originally designed, really, to help diskless workstations boot up, get their config info like an IP address from a server. But BOOTP was pretty static. It didn't really handle dynamic address allocation very well.
Okay.
So DHCP came along and really enhanced BOOTP, made it truly dynamic. It gives out several essential configuration parameters to client devices. Think of it as an automated network assistant, really, with two crucial jobs.
Okay, what are they?
First, delivering host-specific configuration parameters. Things like, subnet masks, default gateways, DNS server addresses, from the server to the host.
The essentials.
Exactly. And second, and this is probably what it's most famous for, a mechanism to allocate leased IP addresses, or sometimes even permanent ones.
So, wow, it's way more than just handing out an IP address. It's like setting up the device's entire initial network identity.
Precisely.
And if DHCP didn't exist, things would get messy really fast, wouldn't they?
Oh, an administrative nightmare, genuinely. Yeah. Just imagine for a second connecting to, say, a public Wi-Fi hotspot. And instead of just logging in, you had to manually type in an IP address, the subnet mask, the gateway, the DNS server address, for every single device you own, every single time you connected.
Ugh, no thanks.
Right. Or think about a network admin trying to onboard hundreds of new laptops or IP phones. Without DHCP, that would be a full-time job just punching in addresses and settings. It's really the difference between self-service checkout and having to ask the librarian for every single book you want to borrow.
Okay, that definitely puts it into perspective. So let's look at it from the user side. You plug in a new gadget or you flip open your laptop and boom, internet access. You just described the problem it solves, but how does that magic actually happen? What's the client doing?
Right, so that's the DHCP client working away, initiating that connection. When your device, laptop, phone, smart toaster, whatever, boots up or connects.
Smart toaster, nice.
Hey, it happens. It doesn't have an IP address yet, right? So it sends out this special kind of message. It's called a subnet-directed broadcast, and it sends it on UDP port 67.
Okay, UDP 67.
Imagine it like shouting into a crowded room, basically saying, "Hello, I'm new here. Is there a network librarian around who can tell me where I belong and give me an address?"
Okay.
The subnet-directed broadcast part just means it's yelling to everyone on its immediate network segment, not to a specific IP, because, well, it doesn't have one yet.
Makes sense.
And UDP port 67 is simply the specific door where DHCP servers are listening for these kinds of requests.
That's a great image. So it puts out this open call. What happens next? That crucial handshake.
Sure.
How does the network librarian respond?
Okay, so that leads us straight into the DOOR process.
Hurrah.
Yeah, DOOR, discover, offer, request, acknowledge. It's the fundamental four-step dance your device and the DHCP server perform.
Okay, walk me through it.
So first, your device discovers. That's sending the broadcast we just talked about, the I need an IP message.
Got it.
Any DHCP server on the network hears this. Second, a DHCP server offers an IP address. It doesn't just assign it yet, it proposes one.
Like a suggestion.
Exactly. Along with other config stuff like the subnet mask, gateway, it's saying, hey, I hear you. How about using this address?
Yeah.
Third, your device requests that specific IP address. Now, if multiple servers made offers, the client usually just picks the first one it received.
Oh, okay.
And it sends a broadcast request to confirm it wants that specific one. This also tells other servers, hey, that IP is taken now. It's like saying, yes, please, I'll take that one.
Right.
And finally, step 4, the server acknowledges the lease. It sends a final packet confirming the IP address, how long the lease is good for, and all the other necessary configuration details. It's the server officially saying, great, this IP is yours for the next, say, 24 hours. Here's everything else you need.
Discover, offer, request, acknowledge. DORA SPICs. Makes sense.
And that 4-step process is really crucial because UDP, the protocol underneath, is connectionless, meaning there's no built-in guarantee messages arrive. DOOR adds that layer of reliability.
That makes perfect sense for a brand new connection starting fresh.
Yeah.
But what if I just, reboot my laptop? Does it have to go through that whole DORA dance from scratch every single time?
No, usually not. Thankfully, that would be pretty inefficient.
Okay, good.
DHCP clients are actually quite smart. They operate in this continuous discovery and renewal mode. So when your system boots up, the first thing it tries to do is renew its existing IP lease. It talks directly to the server it originally got the address from. It's like checking back in with the librarian, hey, I still have this book, can I keep it a bit longer?
Okay.
If that renewal works, fantastic, no DOOR needed, you keep your IP, life goes on.
Simple enough.
But if the renewal fails, maybe the server is down or you move networks or something, then it enters that discovery process again. But even then, it's clever.
How so?
It doesn't just start shouting immediately and repeatedly. It uses something called an exponential backoff algorithm.
Exponential backoff.
Yeah.
Sounds technical.
It just means it sends the discovery messages at increasing intervals. It waits a short time, tries again. If no answer, it doubles the wait time, tries again, doubles it again, up to a maximum delay, usually around 64 seconds between tries.
So it gets less frequent if it's not getting a response.
Exactly. This prevents a device from just hammering the network with requests if something's wrong, which could cause congestion. But it still ensures it gets an IP, just politely and efficiently.
Fascinating. So the client side is all about politely asking, efficiently renewing. Now let's flip the coin. The server's brain. What's a device like, say, a fast iron router actually doing when it's acting as the network's DHCP server, managing all these requests?
Right. The server is the real orchestrator here. In a device like a fast iron router, it's allocating those IP addresses, usually for a specific amount of time, the lease, though you can configure permanent assignments too. And it's constantly maintaining what's called a DHCP binding database.
The binding database.
Yeah.
Okay.
This database is absolutely critical. It automatically maps the unique MS address of each host. That's the hardware address baked into the network card to the IP address it's been assigned.
So it keeps track of who has what.
Precisely. For instance, a pretty robust device like a RUS ICX 7550, our guide mentions, can maintain up to 3,000 of these bindings.
Wow.
This ensures every device has a consistent trackable IP, and crucially, it prevents conflicts where two devices accidentally try to use the same address. It's the librarian's master list. Every book, who has it, and when it's due back.
Okay, so if I'm a network administrator, or maybe just someone setting up a more sophisticated home network, how do I start configuring this digital librarian? What are the first steps to get a DHCP server running?
Well, the process usually starts by just enabling the DHCP server functionality on your router or dedicated server device. That's usually a simple switch or command.
Okay, turn it on.
Yep. Then the real configuration work begins, setting up address pools.
Address pools,
Yeah.
like pools of addresses.
Exactly. Think of them like creating different sections in the library, each with its own range of IP addresses and maybe specific rules about who can get them. For example, you might use a command, like the guide shows, IPDHCP server pool.
Cabo.
Cabo.
Yeah, just a name.
Yeah, Cabo is just a descriptive name. You give that pool. Maybe it's for devices in your office named Cabo, whatever makes sense.
Gotcha.
And within these pools, you define the key parameters. First, the actual range of IP addresses to lease out, like maybe 192.168.1.10 through 192.168.1.20. Then, other crucial stuff. The default lease time, how long a device gets to keep the IP, often it's 86,400 seconds, which is 24 hours.
Right.
You also define the subnet mask, the default gateway address, the router, and the DNS servers the client should use.
All the info the client needs.
Exactly. You can even set limits on how many leases can come from a specific pool, though, as we said, many devices support thousands overall, like that 3,000 limit mentioned. This granular control is really powerful. It lets admins segment networks, reserve specific addresses for servers or printers, and generally manage their IP address space very efficiently.
That's a significant amount of control, just with the basics. But it sounds like DHCP can do way more than just dish out standard IPs. Let's get into some of the advanced features. Auto-provisioning, for instance. That sounds like it goes way beyond simple IP assignment.
Oh, it absolutely does. And this is where DHCP becomes, well, a real cornerstone of network automation.
Yeah.
Auto-provisioning uses the DHCP server for more than just providing an IP. It can automatically tell a brand new device where to go to get its configuration files, maybe its firmware images, even specific boot instructions.
Wow, okay. How does that work?
It often involves using special DHCP options, things like the bootfile.bin option or maybe a manifest file option mentioned in the guide.
Options like extra pieces of information.
Exactly. So imagine this scenario. You plug in a new IP phone or maybe a new network switch instead of a technician having to sit there and manually configure it.
Which takes time.
And invites errors, right? Instead, the device boots up, gets its IP via DHCP like normal, but then it also gets an extra instruction from the DHCP server. Something like, okay, now go to this specific TFTP server.
TFTP, trivial file transfer.
That's the one. A simpler version of FTP, often used for network booting. Up, dot the work. Go to this TFTP server, the instruction says, and download your specific software image and your specific configuration file.
So the server tells it exactly what it needs and where to find it.
Precisely. The device then connects to that TFTP server, downloads those files, and essentially configures and maybe even updates itself automatically.
Yeah.
Think about deploying, say, 1,000 IP phones across a campus. Auto-provisioning like this can slash deployment time from potentially weeks down to days, maybe even hours, and it drastically reduces manual errors. It's a huge efficiency gain, especially for large-scale rollouts.
That is incredibly efficient. Definitely sounds like a game changer for IT teams. Now, with all this automation happening, let's talk security. You mentioned DHCP v4. DHCP must play a role in securing the network too, right?
It absolutely does. And this is an area where, again, understanding DHCP's deeper capabilities is really vital for network health. One critical security feature typically tied to DHCP v4 is dynamic ARP inspection, DAI.
DAI. Okay, what does that inspect?
To get DAI, we need a quick detour into ARP. ARP is the Address Resolution Protocol. On a local network, it's the thing that maps IP addresses, which are logical, to MS addresses, the physical hardware addresses.
Okay, IP to MS.
Right. Now, a common network attack is ARP poisoning. A malicious device starts sending out fake ARP messages. It might claim, hey, everyone, I'm the gateway router, or actually, I have the IP address of that important server.
Uh-oh.
Yeah, if other devices believe these lies, they start sending their traffic to the attacker instead of the real destination. It enables things like man-in-the-middle attacks, where the attacker can eavesdrop on or even modify your traffic.
It's not good. So how does DAI stop that?
DAI acts like a vigilant network guard. It works closely with that DHCP binding database we talked about earlier.
The one mapping MECs to leased IPs.
Exactly. DAI intercepts ARP packets flowing through the switch. For each ARP packet, it checks. Does the IP to MAC address mapping claimed in this packet match a valid current lease in the DHCP snooping binding database?
Ah, so it verifies the claim against the official record.
Precisely. If your DHCP server legitimately assigned IP address 1.2.3.4 to MAC address A, DAI knows that. If an ARP packet comes along claiming IP 1.2.3.4 belongs to MC address B, or maybe claiming an IP that wasn't even leased out.
DAI says nope.
Exactly. It just drops the packet. It doesn't let the potentially malicious ARP message propagate. It's like the librarian checking every book a patron tries to return against the official checkout record. If the details don't match, it's rejected.
That makes sense.
It significantly enhances network security by ensuring only legitimately assigned devices can claim their IP addresses via ARP, preventing those poisoning attacks.
So it's protecting the very identity of devices on that local network segment. That's huge. Okay, one more thing on advanced features. What about really specific devices? Like, say, VoIP phones.
Yeah.
They often need more than just an IP, right? They need specific server addresses or settings to even work.
Yeah, absolutely. And this highlights the sheer versatility of those DHCP options we touched on earlier. DHCP isn't just limited to handing out the basics, IP, subnet, gateway, DNS. There are dozens, maybe hundreds of different defined options that a DHCP server can be configured to provide, carrying highly specific information tailored to particular clients or applications.
So you can customize the information sent out.
Totally. For example, the guide mentions a via IP telephony. For those systems, there are specific standardized options like option 176 and option 242.
Okay. What do they carry?
They carry critical parameters specifically for those VoIP phones. Things like the IP address of the call control server, specific TCP or UDP port numbers the phone needs to use, maybe even the VLAN ID the phone should tag its traffic with.
So all the specialized info they need to function.
Yeah, exactly. The DHCP server can be configured to dish out these precise details just to the phones that need them. This ensures these specialized devices don't just get on the network, but they actually function correctly right from the moment they boot up without manual configuration. And our source material, it even includes a big table stars apparently, listing dozens and dozens of these options. Everything from simple stuff like time servers to really niche vendor-specific information. It just shows how incredibly flexible and finely tunable DHCP can be.
Wow. This deep dive has really opened my eyes. DHCP is so much more intricate, so much more powerful than just being the IP address dispenser I might have initially thought.
Right.
It's woven into everything from just getting you online to automating massive device deployments and even providing fundamental network security. It really is like that invisible backbone.
Yeah, it really is. It keeps our digital world connected and, importantly, coherent. We've seen how clients start their journey, that Dora dance. How servers intelligently manage these huge pools of addresses using those binding databases. And then how these advanced features like auto-provisioning and DAI bring efficiency and security. It's really a testament to smart network design, isn't it? Allowing all these complex devices to just work without forcing every user to become a network engineer.
Absolutely. And for you, our listener, hopefully this knowledge gives you a better appreciation for the fundamental logic that underpins almost all the digital communication you rely on. Right. It's kind of the difference between just seeing a light turn on and understanding the entire electrical grid, the transformers, the wiring that actually makes it happen.
That's a good analogy.
It reveals how these intelligent automated systems keep our incredibly complex digital world running, often without us even realizing that intricate dance is happening constantly in the background.
Which, leads to maybe a final thought or question for everyone listening. Given the sheer number of DHCP options available and the depth of configuration possible that we've just scratched the surface of, think beyond just getting an IP address. What specific, maybe often overlooked DHCP setting or option could you investigate? Something you could perhaps implement in your own network, whether that's just your home setup or a large enterprise environment that might unlock a new level of efficiency or security or maybe some specific functionality you haven't even considered before.
That is definitely something to chew on. What hidden potential is sitting right there in the DHCP settings? Great final thought. Keep exploring, keep learning, and please join us next time for another deep dive.